Everyone, so welcome back for the afternoon session. And today we're very happy to hear from Raghu Meka from UCLA, who will be telling us about learning Gaussian graphical models without condition number bounds.
Hi, everybody. Today I'll tell you about Gaussian graphical models, which kind of continues the talk that Ankur gave today morning. He was talking about graphical models, learning graphical models when you have latent variables. In this talk, I'll take a different dimension where we're still talking about learning graphical models, but this will be in the space of continuous graphical models. We have all the variables, but we have very different constraints and different challenges. And this is joint work with John Kellner, Freddie Kohler, and Ankur, who is here from MIT. Okay, so the talk has three parts. First, I'll talk about what GGMs are, why are we studying them, and then the special models and the specific algorithm that we're going to study, which is in this box here. And then I'll say a few words about what we can actually analyze about this algorithm. So what are GGMs, or Gaussian graphical models? If you're me, they're just a fancy word for multivariate Gaussian distribution. Everyone knows what a multivariate Gaussian distribution is. And usually when we think of a Gaussian distribution, we parameterize it by the covariance matrix, right? So in this talk, I'll follow statistician's notation. So the number of features, the dimension that we're working in will be P, okay? So you have a p-variate, multivariate, multidimensional Gaussian distribution. Covariance matrix is sigma. And usually we never think about the formula of the PDF of the Gaussian distribution, but I wrote it down here because there's some reason this sigma inverse will show up, all right? The twist today is that instead of talking about GGMs where we instead of talking about Gaussian distributions, parameterize the covariance matrix, today we'll talk about parameterizing them by the inverse of the covariance matrix, which is called the precision matrix. So theta, which is sigma inverse. And why we're studying the precision matrix, this goes back to this very nice property of Gaussian distributions from, I think, identified by Dempster in 72, that the precision matrix encodes the conditional independent structure of the Gaussian distribution. What do I mean by this? So you have the precision matrix, which is sigma inverse. Then the dependency graph of the distribution is exactly the support of the precision matrix. Okay, and dependency graph also showed up in Ankur's talk. Basically, it encodes the Markov property of the distribution. In what sense? You take your precision matrix, build a graph where two vertices are adjacent. If the corresponding entry is non-zero, then whenever the entry is zero, those two variables are independent, conditioned on the neighbors of one of the vertices. Okay, so this is the Markov property that holds for the distribution with respect to this specific graph. Okay, so for instance, here, x1 and x3 would be independent, conditioned on the neighbors 2 and 5. And another reason we're going to look at the precision matrix is that we're going to parameterize the complexity of the distribution very differently, right? So we have a p-variate Gaussian distribution, but we're going to assume that the distribution is simple in the sense that the precision matrix or the max degree of the support graph G is small, is D, which is much less than P. It's kind of the same setting as we saw in the previous talk. Okay, and this is the assumption that makes talking about precision matrices meaningful or interesting, that this condition that the precision matrix is sparse is very different from what you get traditionally by looking at the covariance matrix. Why are we looking at these GGMs? Well, there's a very nice model for various statistical relations between variables, especially in applied sciences. I found many applied works which use GGMs to model the distributions that they're facing. And people also have used them for various network data, but I don't want to go into these things too much today. And the bigger picture that we're looking at in previous talk, this talk, and maybe a little bit even in the next talk is, I give you some distribution, right? Under the assumption that the dependency graph, as we defined before, is sparse, can we learn the distribution? Can we learn the dependency graph from few samples? Okay, this is just like learning Markov random fields, learn undirected graphical models. All of these are rephrasings of the same question. For instance, in Ankur's talk, we talked about learning easing models, right? So you have a distribution 1 minus 1, and you have the dependency graph. And under some conditions on the dependency graph, you want to learn the distribution. All right, there's a lot of work on that. But today we're going to talk about the continuous flow, where the problem is different, but also I think a little easier in terms of upper bounds. Okay, so I'd like to give an example that you should keep in mind. This will be the running example for the talk, and also I think something to play around in your head with. So suppose you have a p-varied Gaussian distribution, which is generated as follows. I generate p independent Gaussian distributions, z1 through zp. These are IID. But then the actual variables that you observe are the prefix sums, right? So xi is xi minus 1 plus zi. So the first sum of the first I zi's is xi. Okay. Now, what is the covariance matrix of this distribution? You can just do some arithmetic to see that it has this seemingly simple structure, but it's kind of very dense. What is the precision matrix of this distribution? Any guesses? Yeah. Yeah. So if you look at the precision matrix, you exactly get this matrix, right? It's very simple. It's 3 sparse. Each row or column only has 3 non-zero entries. And the dependency graph is just line graph, right? It's just packed. Okay. And it kind of makes sense. And it's like a Markov chain in that once I give xi minus 1, what you see afterward is independent of the past. In the context of learning sparse GGMs, there are 2 questions. One is structure learning. Given samples from this distribution, can you learn the dependency graph? The other question is parameter learning, where I want to learn a Gaussian distribution which is close to my samples in some way, or maybe even estimate the precision matrix entries exactly within some error. Okay. So structural learning is just, you're given samples, x1 through xn, n is the number of samples, and I'd like to output the dependency graph of the GGM. This is what we're trying to do. And the challenge, as I said often, is that, especially in the context of Gaussian graphical models, that the number of samples you have is much less than the ambient dimension p. What can you do in this case? For Gaussian distribution, if you have linear in the dimension many samples, you can do whatever you want. You can estimate the covariance matrix really well. Then you can invert it, make a standard Gaussian. You can build a basis, do whatever you want. But we're in the case where the number of samples is going to be much less than the ambient dimension. But this is still a meaningful question to ask because of our assumption that the precision matrix is sparse. So that kind of saves us here. So in summary, the question we're studying is the following. I'm giving you n samples from a multivariate Gaussian distribution, where n is now much less than the ambient dimension. You should typically think of it as logarithmic in p. And we'd like to find the dependency graph of the Gaussian distribution. All right. Okay. And as I said, once you know the dependency graph, you can estimate the parameters easily because then it becomes a d-dimensional problem instead of a p-dimensional problem, and you can do standard stuff there. Yeah.
When you write O sub d, do you mean it's linear?
Oh no, it's some function of d in front. That's fine. The main thing we are shooting for the first step is to get logarithmic dependence in p. In fact, in our bounds, at least the dependence is going to be d log p or d squared log p or something like that. So it's not bad.
Okay.
But as I said, the biggest thing is it logarithmic or linear in the dimension p? Okay. Any other questions? Okay. So let's go back to our example, right? Just kind of instantiate a version of this problem. Earlier, we had the random walk distribution. Now, suppose that you're looking at the same random walk example, but it's a random walk in some permuted order. There's some unknown permutation pi, and what you're saying is, x pi of I is x pi of I minus 1 plus di. So it's prefix sums, but under this permutation. You don't know the permutation. All you're saying is the variables, samples from this distribution. How many samples do you need to recognize the permutation, to learn the permutation from this? You can do the same thing again. The dependency graph is still going to be a path, but it's some jumbled up order, and you have to find out what the order is. How many samples do you need to find the hidden permutation? Okay, very simple, concrete question. Algorithmic and kind of, even from a statistical standpoint, it's interesting. How many samples do you need? And how much time do you need to find such a permutation? right? Okay. So, I mean, GGMs, as I said, has been very well studied in the statistics literature. There are a lot of papers and also some popular software packages like Lasso, CLIME, and CLIME, and so on, which are used across various fields. And one of the most used ones is this package called Lasso. And what they show is that you can indeed learn the dependency graph with very nice sample complexity, d squared log p. So it achieves this logarithmic dependence on the dimension, but they need a strong assumption that the precision matrix is incoherent, okay, under some sense, which I'm not keen on defining now in the interest of time. But this is a strong assumption that is violated by the random walk model that we just looked at. Okay? In fact, it's violated by most models when you have long-range correlations. And similarly, there's this work based on linear programming, which can also learn the dependency graph with logarithmic and p dependence on the dimension. And there's some m to the 4 where m is some kind of condition number, which is the maximum ratio of the entries in sigma and theta. Okay. So in both of these cases, the incoherence or this ratio of entries in sigma and theta is some notion of condition number of the distribution. And once again, this is violated by the random walk example that we just saw. And so the previous works were only known to work under well-conditioned precision matrix scenarios. And this is not just that the analysis doesn't work. The algorithms actually do fail empirically when you take simple twists of the random walk model. So there's it's not just a matter of getting better analysis. So before going on, let's first ask ourselves, is it even possible information theoretically? Or what is possible information theoretically? And this was made precise in a very nice work by Mishra, Woofre, and Loka in 2018, who gave a almost precise characterization of what you can learn and how many samples do you need for Gaussian graphical models. So to make this, to define this, I need to introduce a parameter, which I'll call kappa. And there's a formula here, but what it essentially measures is the signal that is present in any 2x2 submatrix of the precision matrix, okay? Or in other words, let's say I'm trying to identify an edge ij, how strong is that edge with respect to the corresponding variances, right? Can imagine if this entry theta ij is very small with respect to the variances, then it's very hard to identify. So this is a parameter, and the nicest thing here is it only depends on pairwise submatrices or 2x2 submatrices. How strong is a single edge, and not on the global structure of the entire distribution. And so it just measures signal in 2x2 submatrices and not the whole matrix. And what they showed is that under this definition, information theoretically, d log pure kappa squared samples suffice to identify the dependency graph. Okay. And for instance, if you go back to the random walk model, this parameter kappa is exactly half. Okay.
So just to clarify, when you say identifiable with the sample size, do you mean that you can bound the probability of an error for the whole precision matrix?
You can identify the dependency graph. So it will be something like, okay, with d log pure kappa squared times log 1 over delta samples, maybe. With probability 1 minus delta, you'll output a graph, which is exactly the true graph.
Okay, thank you.
There's a failure probability in term which depends on log 1 or delta and just condition on the samples. Okay. So you can see that for random walk model, this kappa is half. So you should be able to identify the unknown permutation with only logarithmically many samples. And this is also tight in some sense, in that there's a lower bound due to Wang, Wainwright, and Ramachandran, show that you do need log p or kappa square samples to identify the graph. But there's a catch in this result, in that the runtime of the algorithm is p to the O of t. It's polynomial for fixed degree d, but it grows as the degree grows, the runtime grows. And the reason this p to the O of d kind of shows up is you're essentially enumerating over all possible neighborhoods of a single vertex, and then you kind of rule out which one is the true one and which one isn't the true one. Okay. So the main question that we address in this work is, when can you beat this enumeration of all possible neighborhoods? Can you get a runtime which is a fixed polynomial in P even for large D? Can you get runtime even P to the little o of D? So we want to use logarithmic in P many samples. Runtime should be a fixed polynomial in P. And the main thing we do in this work is that the answer is yes for a large class of models. The information-theoretic result applies for all Gaussian graphical models, and our result applies for a large class of models which have been studied in various contexts within statistical physics, for Gaussian graphical models and other things. Okay. So, and also I'd like to say that the algorithm is very simple, and it also recovers the guarantees of Lasso and CLIME. So it's kind of strictly more general than the previous algorithms that were used. Okay. So that's the question that we're going to study and the motivation. And now let me tell you about what the algorithm is and what are the special models for which we are able to prove that it works. The first model is attractive GGMs, which is again a little bit like the ferromagnetic assumption that we saw in Ankur's talk. And here we say a GGM is attractive if all covariances are non-negative. Okay, meaning all variables are positively correlated. Okay. When you invert the matrix and look at the precision matrix, it translates to saying that all off-diagonal entries in your precision matrix are negative. And this shows up in Gaussian free fields and has many applications for Gaussian processes. In particular, the random walk example that we saw is definitely an attractive model. The off-diagonal entries were just -1 or 0. This was a random walk model, and it's an attractive model. And even though it's an attractive model, it's kind of simple, it is ill conditioned as long as the graph has long paths. So the existing results do not apply even for these attractive models. And the lower bound also applies here for attractive model. Lower bound of log P applies here. Yeah?
If you go back to the previous slide.
Sure.
What happens? Do you get these attractive GGMs if you consider generalizations of the random walk model? So instead of having just a Markov chain, you have other types of dependencies between the variables?
You mean like, maybe prefix sums? As long as the coefficients in your equations are positive, I think you get attractive model. I mean, yeah, in terms of precision matrix, it's a little bit difficult to interpret. But in covariance matrix, it's easier. As long as any two variables, their correlation is positive, it's attractive. Okay. And what we do is give an algorithm which we call greedy prune, and we'll see it learns attractive models with d log p or kappa square sample complexity, which is kind of what we were shooting for. And the runtime is only quadratic. And the more general class of models that we study are called Walk-Summable GGMs. And this is a bit of a technical definition, but it does arise in many other contexts. So when is a GGM walk-summable? Well, you start with your precision matrix. You have the precision matrix here. You have all the diagonal entries and the off-diagonal entries. You take every off-diagonal entry and make it negative. Okay, I get a new matrix. The original precision matrix, because it is coming from a Gaussian distribution, it is positive semi-definite. It's the inverse of the covariance matrix, which is PSD. So it is PSD. Whenever this operation preserves PSD-ness, we call the matrix walk-summable. Okay, so I replace every off-diagonal entry with negative absolute value. If the resulting matrix is still positive semi-definite, then the original matrix is walk-summable. Okay. And this was introduced in the context of statistical physics, but there are many classes of GGMs which are studied in the literature which fall under this umbrella of walk-summable models. For instance, you can take attractive models. All their off-diagonal entries were negative to begin with, so the operation does nothing. Okay, you can take something called pairwise normalizable models or non-frustrated models. And if you're coming from theory literature, if you think of symmetric diagonally dominant matrices, they're all walk-summable because the guarantee that their PSD is very much only depends on the absolute value of the entries. Okay. So these models were studied in the context of learning GGMs, and the best algorithm was again something like P to the O of D. And this was known even before the work of Mr. Buffet and Loco. in 2012. And what we do is, what we show here is that the greedy prune algorithm learns these models also with logarithmic in P dependence. And the dependence on degree D and kappa kind of is worse than for attractive models, but they're still polynomial. And the runtime is again quadratic. All right. And as a caveat, we can actually improve it further to get it to D log P over kappa to the 4 by a combination of the greedy algorithm that we're going to see and the L1 minimization algorithm. All right. So let me now tell you what the algorithm is. This is very similar in spirit to the one that Ankur described, where we're going to use a greedy approach to build the graph. So just to recall, the setting is we have samples from a GGM X, and we're trying to build a dependency graph of X. So the algorithm has two phases where, let's say, forget the entire graph. I'm just trying to figure out what are the neighbors of a single vertex. And I want to identify what are the neighbors of vertex 1. I'll do this in parallel for all the n vertices. And in first phase, I'll grow a candidate neighborhood. I'll pick a bunch of vertices, which I think will contain all the true neighbors. And in the second phase, I'll throw out some of the vertices. So how do I grow a neighborhood? Again, we're trying to focus on vertex 1. And the way we grow the neighborhood is very simple, a simple greedy rule. And the greedy rule is as follows. As long as the set of vertices picked so far is small, I pick a new vertex, which gives me the most bang per buck in terms of reducing the variance of the vertex that I'm trying to build a neighborhood of. In other words, I look at the variance of x1 here, conditioned on all the vertices that I already added, plus the new vertex j. Whichever j minimizes estimate, I'm going to add that to my set of vertices. The idea is that conditioning on the neighbors should reduce your variance the most. Conditional variance. Okay. And that's the algorithm. I mean, I'm using true variance as a number here, but you can use estimations for that in your algorithm, and it doesn't change too much. And interestingly, if you're familiar with computer sensing literature, this algorithm is actually equivalent to something called orthogonal matching pursuit. Just as an aside, it just happens to be the same as OMP, which is very nice. Okay. Now, once I have the neighborhood, what do I do with it? Well, so you might overshoot the set of neighbors and have some spurious neighbors. So we just throw some of the neighbors out, some of the vertices out. And what do I do for throwing things out if they are useless? I mean, okay, so if dropping a vertex does not hurt the conditional variance too much, I just drop it. Okay, so it's kind of throwing off all the dead weight. And once again, we're using estimates on the conditional variance and just keeping those which are really helpful in maintaining the variance. So that's the entire algorithm. And just to give an example of what happens when you use this in practice. So here's a case of GGMs where I have a single long path, just like the random walk example. But then I also have some cliques, some 4x4 cliques thrown in. It's a very simple instance. The precision matrix is path plus cliques, kind of looks like this. You have zeros almost everywhere. You have a small patch of non-zeros along the diagonal, and the max degree is 3. It is an ill-conditioned GGM. When you run the algorithms, this is what happens. So the greedy algorithm kind of really recovers most of the graph exactly. The other algorithms have some non-zeros on the off diagonals. Okay, and you can plot this further and check how many samples does each algorithm require to identify the graph with reasonable certainty. Okay, and by changing the intensity along the cliques, you can defeat all the other algorithms. But the greedy prune algorithm kind of almost always grows. The dependence on the dimension is logarithmic. Okay. For instance, here you can see that CLIME package, the dependence on the dimension in terms of number of samples needed is growing nearly linearly, whereas greedy is flat, and Lasso is also flat. But then if you change the intensity, the other one fails, whereas greedy still works. All right. So let me get to the interesting part, which is how do we actually prove these theorems in the last 5 minutes. I'll give you a hint of what goes into them. So just to recall, here are the two main things that I talked about. Greedy prune learns attractive models with d log pure kappa squared samples and runtime. And for walk-summable models, it's worse, slightly worse at d squared log p or kappa to the 6. And as it also requires Lasso and CLIME guarantees when you have the incoherence or condition number assumptions as before. Okay, so about the analysis. The analysis for attractive models is much easier and kind of follows from this concept of supermodularity that Ankur mentioned. So if I can define a function on subsets of vertices, which is the conditional variance of x1 given xs, given all the vertices in all the values in S, what happens to the conditional variance. And this function turns out to be supermodular. It was known before. And once I know it's supermodular, the definition is here, I can use greedy algorithm to run it, right? Just as before, if I have a supermodular function, I can maximize it. And you have to maybe spend a little bit of time to make sure that you can do it with samples, but that's not too difficult to do. Okay, we don't have exact access to the function f of s. We have an approximate oracle for it, but we can manage to do it. And the issue, though, is that when we go to a slightly more general case of walk-summable models, this function is no longer supermodular. Or there are various weakenings of supermodularity under which we do know greedy algorithms do work, but none of those conditions hold. So why does greedy still work for walk-summable models, even if you don't have supermodularity here? And here we use a connection to symmetric diagonally dominant matrices. And the punchline is that for walk-summable models, under some suitable normalization, knowing a single neighbor gives you a lot of mileage in figuring out the entire neighborhood. Okay. Let me illustrate this, and I'll skip this for now. Okay. So one special case of walk-summable matrices are symmetric diagonally dominant matrices. And these are matrices where the diagonal entry is larger than some of the off-diagonal entries. Okay, this is kind of essentially guarantees that the matrix is walk-summable. Now, for all of these matrices, for any vertex I, there exists a single neighbor that once you condition on, all the conditional variances drop down dramatically. They now only depend on kappa squared. So there exists a neighbor that is comparable to conditioning on the entire neighborhood. Okay. And the whole problem in this setup of Gaussian graphical models is that the individual variances can be much higher than the conditional variances. Whereas this bound is saying that there is at least one neighbor where once you condition on it, all the conditional variances are kind of bounded. And if they're bounded, small, which don't depend on P, we can detect it with few samples. Okay, and the proof of this uses the triangle inequality of effective resistance metrics on graphs and properties on conditional variance. So it kind of connects to this literature on effective resistance on graphs. Okay. So in the last 1 minute, let me tell you one special case of this bound. So for intuition, assume that you have a precision matrix where the diagonal entries are 1. I'm just normalizing it so that this is true. Then the condition kappa translates to saying that every non-zero off-diagonal entry is at least kappa in magnitude. They're not too negligible. And the lemma says that under this condition, the conditional variances are bounded by 1 over kappa. Okay? So they cannot be P or P squared or anything like that. So that's the main thing. So for instance, if you go to the random walk model, the variance of the vertices on the right or in the middle are linear in the dimension P. Variance of xp over 2 is P over 2 plus 1. Okay. But the conditional variances, wherever you're on the line, is still just 1. Right? So this is a dramatic drop between variance versus conditional variance. And this lemma is saying this holds for all SGD precision matrices. And this is not true for general sparse precision matrices. It's only true for this special case of matrices. Okay, there's a proof here in quotes, which I'll leave it at that. Okay, so to summarize, we studied this question of learning GGMs. And the main question, as I said, is assume that the pairwise correlation is constant. Can you learn it in runtime p to the little o of d and sample complexity that is, as long as it's sublinear in p, I'll be happy. And we saw a simple greedy algorithm. We solved interesting special cases. And there are a lot of open problems here. Can we solve more general class of models? I don't even know how to test if a model is correct. I give you samples from a distribution. I give you a model. I give you a graph and a precision matrix. Tell me, are they the same? What happens if you have hidden variables? And I actually think that the problem is computationally hard in general, but we really don't have any evidence for this. My conjecture is that there's no p to the little of the algorithm to recover the structure of GGMs with these many samples. We'll stop with that.
Quick question or two, and Freddie, set up.
So I'm just curious, so a very similar algorithm arises in learning directed graphs. And so I'm wondering if you have any sense for if the Walk-Summability criterion is how close to necessary it might be for these greedy algorithms to work.
So we were able to consider examples where greedy would fail. So I don't know if it's exactly necessary for the graph to be walk-summable, but there are simple cases where the greedy algorithm would fail. So yeah, that's a very good question that, we still, at least I don't have a very good sense of what the hard problems should be here. And that's a good thing to have. Like, we need a set of candidate models, which we think are computationally hard. All right.
All right, so continuing the afternoon session, we have Freddie Kohler speaking, who I guess, was at MIT at the time, but is now at Stanford. So please take it away, Freddie.